All right, so we're going to video all of this, so that means I've got to stay in this region, which is fine. But we're going to talk about a different way of programming, something called state transition programming. And the example I'll use again is the silo simulator, but then we're going to do everything we've done so far with the bottle line simulator. It's going to take us not just this class, but the next class as well to get all this done. And it's quite a bit, so you'll probably want to take notes. There's nothing about this in the slides. There's nothing about this in the book. This is something I've learned that is very powerful, very useful, and it really saves you, I won't say it saves you a lot of time, but it saves you a lot of brain power in algorithm development. Remember that video I showed you guys of the little car that made it through the maze, balanced and all that? That used a state machine. And the idea behind this is that basically the machine stays in particular states. Remember, we've talked so far about the PLC and the interaction between the PLC and the mechanical or the physical system. And we noted that the physical system takes a long time to respond, right? The PLC is very quick. It reads whatever the inputs say, it sets the outputs immediately, right? It's very, very quick turnaround time. But like with the silo, it takes time for the box to go along the conveyor and finally come into position beneath the silo where it's ready to be filled. So basically, the program needs to stay in one state for a long time. Leave the conveyor motor on for a long time. Does that make sense? So the way we start a state transition machine, a state machine is with a state transition diagram. So let's start, and usually the way you do this is you just make circles that indicate the states, and all this will become more clear as we go, but please stop me and ask questions if there's something you don't understand, okay? So let's call the first state the get box state. Now in this state, remember the box starts off to the left, right? Remember that? It starts off to the left. The get box state, what do we need to do, dear? What should the outputs be? If we're trying to get a box underneath the silo, what should be on, what should be off? Motor should be on, right? So let's say, and the outputs are associated with the states, okay? Because most of the time it stays in a particular state. So let's say motor equals 1. What about the valve? Should be off, right? So valve equals 0 for off. Now, we're doing the same thing. You already know what the solution should be like. You already know that it's just the motor and the valve that we're interested in, the repetitive part of this process. You know all we're interested in are procs and level. That hasn't changed. That's still going to be the case, okay? Because we're still dealing with the same repetitive box filling cycle, okay? So get box, when we're trying to get a box over beneath the silo, the motor should be on, the valve should be off. Okay, fine. Now, that's all well and good, but what allows us to change from this? Because what we're going to do is we're going to transition out of this state into another state. So what are the conditions? What are the input conditions that mean we no longer want the motor on and the valve off? Well, when prox goes to 1, right? Think about it. If the proximity sensor is triggered, in other words, if a box comes into place, then we need to move to a new state. We don't want to leave the motor on at that point, right? We're not getting a box. We've got a box. We've succeeded. We've accomplished the purpose of this state. Now we're going to come back to it later when we go to get the next box. But for now, we've got a box. What do we want to do now? Well, we want to fill the box. And see how this breaks down naturally? Get a box, fill the box. It makes sense, right? And that's one thing that's nice about this state transition stuff. In that case, to fill the box, of course, the motor would have to be off and the valve would have to be on. Now this is going to be one of the simplest state machines that exist. But I'm going to show you something. I'm going to add something to it at the end that will make it a little more interesting, okay? All right, fill box. Now, what is it? How do we know that the box is full? What happens?
Level sensor.
Level sensor comes on. So we're going to move out of this. What do we want to go back to the fill box state? Or I'm sorry, the get box? No, we have to clear the box, right? So, because if we just went back to the get box state, procs would be true, we'd go back to fill box, right? Doesn't make any sense. So we've got to leave this state and go for another state. So this is, like you said, when level is equal to 1, right? Okay, the next state would be, I would call it a clear box state. You could also call this a full box state. In other words, we've got a full box right now. What do we want to do with that box? We want to send it on its way. Okay? So in that case, I guess I'm not using the word state, but these are states. Each of the circles represent a state of the machine. In the state, we leave the motor on and the valve off. Okay? So this kind of makes sense. I mean, it's the same thing we've been doing all along, just looking at it a different way. And notice that there's memory built into this because we're in a particular state. We know that we had a full box because we reached this state, right? So we don't really have to set bits. In fact, our program will have to know what state it's in, and we'll have to define all of that. But we'll do that, and those bits will basically serve as the memory bits instead of setting a bit somewhere to say, hey, there's a full box, and then once it's cleared out of the way, then we don't have a full box. So what allows us to move out of this? Well, we could go back to the get box state if prox goes to 0, right? Because once the prox is cleared, that means that full box is out of the way. As far as we're concerned, we're done with it. It's time to go get another box. This is a very simple state machine. It looks just like the sequence we had, right? Remember we had a 3-step sequence? Get the box, fill the box, clear the box, return, keep going. The power of a state machine versus that sequence program that I gave you guys is that you can go to any state at any time with the right conditions. For example, let's add another state. Let's call this the stop state. Now we wouldn't have to do it this way, okay? We don't have to do it this way. We could simply use a seal-in circuit to operate the start-stop buttons. But for the sake of showing you how to do this and the power of a state machine, I'm going to have a stop state. And it turns out we don't have to go to the next step. We don't have to go in sequence. We could simply go directly to stop if the stop button, now the stop button's normally closed, right? So when it's pressed, that's a 0. Okay? Right? You push the stop button, which is normally closed, that's going to break the contacts, which means stop goes to a 0. This is the stop button. Let me make this stop button and make that clear. So if the stop button is pressed here, we want to go to the stop state. Well, same thing here. If stop button is 0, we need to go there. If we're here and the stop button is pressed, then we need to go to the stop state. How do we get out of the stop state? And where would we want to go? Well, I would think that we would want to go to the get box state if the start button is pressed. Okay. Does that make sense? See how we can transition to any state we want? We just have to define this. Now, I understand that you don't know how to make a program from this yet. That's okay. This is the first step. This is where you define how you want the program to work. For example, there's one potential problem. Let's say that a full box comes along. We're in the get box state. Prox is triggered. Okay, we're going to go to the fill box state. Now remember, the mechanical system cannot respond near as fast as the PLC can go through its sequence. Okay? As soon as the PLC goes to the fill box state, it's going to be looking for either level to be true or stop button to be pressed. If it sees a full box come along, it's going to go to this state for a millisecond or so, right? And it's immediately going to go and say, this is a full box, let's clear it. So this works. See, I could have a condition here. I could say level equals 0 as well. I could do that. It turns out the more conditions you have for the transitions, the more difficult it is to program, the longer it takes to program. I prefer to have as few conditions for the transitions as possible. I also prefer to have as few transitions from states as possible. But to illustrate this process, I'm going to make a 4-state state machine. 1, 2, 3, 4 states. Okay? And I'm going to use just the minimum conditions for moving, realizing that if we do go to this state with a full box, it's okay. We'll go back to the get box state very quickly. Okay, so there will be a fraction of a second where the PLC tries to turn the motor off and the valve on. Those things won't have time to respond anyway, so it's okay. It'll go to this state very quickly and it'll turn the motor back on, the valve off, and continue. Now, it might make the relays clack or chatter a little bit. That's possible. Not likely even, because if the PLC scan time is on the order of milliseconds, even the electrical switches aren't going to respond very quickly. So if you set this up, it was working, and the people running the line were complaining because, hey, this relay, every time a box goes by, it makes a little snap noise. What's going on? Well, it's just this. Okay, maybe that's a problem. Maybe add in the condition and change your state machine. Okay, it's a lot of work, but you could do it. Anyway, so these round circles are called the states, and that's where you expect the machine to spend most of its time, not in the transitions. The transitions are very quick. Okay, the transitions, here's something I want you to write down. All of the states go with outputs. Notice how we have the outputs in each of the states. I should add this one here. So you have to decide what should the outputs be in all the states. What do you think the motor and valve should be?
0,
0, 0. Right? They should both be off. So the states go with outputs. The transitions are driven based on inputs. Okay? So there's a state, for example. Let me use a different color because that looks like a transition. So I can't make lines to all these, it would get too messy, but you get the idea, right? So states are associated with outputs, whereas transitions are associated with inputs. So how do we program this mess? Well, it's actually not too bad, it just takes a little bit of work. Now, I'm not sure what to do with the video, because this is going to be a pretty boring part if you're trying to watch the video. You do need to hear me talk, so if you're watching the video, I'd recommend that you open up the spreadsheet that I'm going to post, because we're going to put a ton of the design work into a spreadsheet. Now, if you guys want to create your own spreadsheet here in the class, you're welcome to. You don't have to. I will post the spreadsheet for you. Okay? Now, understand that this is all up to us to program, define, decide how it works. Okay, that's on us. PLC is just a dumb machine that'll do whatever we tell it to do, if we tell it right, and ask it nicely, right? Use the right syntax. You have to talk to it just right. Well, that's okay. I'll show you how to talk to it. But the first thing to do, really, one more thing for the video, the first thing to do is to define what I will call state bits. We have to somehow distinguish between these. So let me define 2 bits. What 2 bits? Well, I don't know. Let's just say the state bits are going to be, well, we'll have the bit at 0/0 and the bit at 0/1. Why did I choose 2 bits? I chose 2 bits because I've got 1, 2, 3, 4 states. And so watch this. If I have the stop state to be B0 = 0, let me abbreviate 0/0 as just B0. We're going to have to write it many times. And I have B1 = 0. If I define those bits and say when B0 is 0 and when B1 is 0, then I'm in the stop state. Then I could differentiate the rest of the states. In fact, I could call this the B0 = 1, B1 = 0 state. And then I could call this the B0 = let's see, what do we got? 0, that should be fine. B1 = 1 state. And then I've got one more combination available, and I could write B0 = 1, B1 = 1. And I'm sorry, I'm putting it in and out of the state, but the point is that these bits are associated with the state. In other words, this is how the PLC knows what state it's in. So we've got to somehow set these bits appropriately so that the machine will go from one state to the next the way we want it to. So let me make that clearer. Do you see how these 2 bits are kind of like a name for each of these states, and each name is unique? They're different. Well, what could we do? Well, I purposely made the stop state the 0/0 state because when you first turn on the PLC, the memory is going to be clear, right? And I want the machine to start at this state. I don't want it to just take off and start running when I first turn it on. So whatever state you want it to start in, make that your 0/0 state. And if I wanted to add more states than this, I would need one more bit, right? In fact, if I had one more bit, how many states, how many unique names could I make by counting a binary with 3 bits?
8.
8, right? Do you see how that works? If I had one more bit, I could have 4 more names that are unique, right? That would be like a B2 equals 0 for all these, and B2 equal 1 for all the other states, whatever they be. Since I only need 4, I only need 2 bits. Since I only need 4 states, I can get away with 2 bits. And that'll make our lives easier. Okay? Now, what else did I want to tell you about this? So I have to somehow figure out how to do this, right? This condition here is what drives the change of these bits. In fact, if the start button is pressed, my problem is reduced to somehow changing B0 to a 0 and B1 to a 1. Well, B1 is already a 0, so all I would have to do is set B0 to a 1. If somehow, when this happens, if I can set up logic that will turn on bit 0 when that happens, that will make me go to that state, because that's the definition of the state. Make sense? Please ask questions. I see questioning looks. I know this is a lot to take in. So how would I do that? Well, I would go into Excel and start designing. Now let's collect a few things first. Let's just put all our ducks in a row and figure out what outputs and inputs we're dealing with. We'll start with inputs, that's fine. Over here I'll write down outputs. It's always important to know exactly what inputs and outputs you're dealing with, obviously. All right, so let's start up Logix Pro and go into the silo simulator, because I can't remember the addresses. Got to tell Merlin to be quiet. There we go. All right. Now if I go into the silo simulator, it appears that the inputs of interest, there are actually 3. There's the proc sensor, there's the level sensor, and then we also decided to put actually there's more than that, there's the start and the stop button. I'll put these in order in a moment once I know their actual addresses. The proc sensor is at I:1/3. The level sensor is at I:1/4. Start button, I don't remember, let's see, 1/0, so I:1/0. Stop button must be 1/1. Yeah. So I:1/1. So there are the addresses of all the inputs that are related to all the transitions. See how I've collected them all together? I need to be able to deal with the start button, the stop button, the level, and the procs. Okay. What outputs will I control with this state machine? Well, the outputs I will control are the motor and the valve. The motor is at output address 2/0, and the valve is at address O:2/1. So now we've got everything set up. I'm going to put the inputs in their proper order. So we'll have 0, 1, then 3, 4. They'll be ascending. Just like the outputs are in ascending order also. And that's just so I can reference them. Okay. Now, I'm also going to name the states. Notice basically what I've done so far is work with the transitions, the inputs. So the states, well, we've got the stop state. You can also call the start state, right? Because that's where we begin. So let's just name it the stop/start state, since we've got the space in Excel to do it. There's, what other states have we got? There's a get box state. There's a fill box state. There's a clear box or a full box state. The bits I will deal with are bit 0/0 and bit 0/1. So help me out here. On the start-stop state, what are the bits set to?
0 and 0.
0 and 0. In fact, that's really the definition of the start-stop state. When bit 0 is a 0 and bit 1 is a 0, then that means the machine is in the start-stop state. And we can use that in our logic to calculate the next state. And we'll see how that works in just a minute. The get box state, what do the bits look like for that state?
1 and 0.
Well, be careful.
Well,
It's
the way
bit
you-
0 equal 1
Yeah.
and bit 1 equals 0. Okay, the fill box state. It's just the opposite, right? So bit 0 is a 0, bit 1 is a 1. And in the clear box state, both are 1s. Let me, again, well, they're already, I guess, organized in ascending order. So see how we just counted in binary there, basically? That's all I really did. We got the 0, 0, 1, 0, 0, 1, 1, 1. It's all the combinations. So what am I doing here? Well, I'm just making sure that I know the labels that I'm using, how do they relate to what the program is going to talk about. Does that make sense? Just like the program couldn't care less that I call I1/0 start, but anyone reading my code would like to know that, right? That's the start button. So the names I'm assigning here are just names for our own convenience. Okay, so how do we program this? Well, what you do is you set up the logic for each of the transitions. Let me show you what I mean. What we want to do is, if we're in the get box state, and that's a big thing, if we're in other words, when we're in this state, then if prox is 1, set the bits to this. The nice thing about it all, and the magic of this that makes your life easier sometimes, is that you only have to program 1s. You don't have to program 0s. Okay? Now, I'll show you what that means. Let me write in blue, and we'll see if we can set up an equation here. All right, these are the conditions, right? If B0 equals 1, and, that's a logical and, B1 equals 0, and prox equals 1, then B1 equals 1. That's a logical statement, right? In fact, we could write a line of ladder logic like that. Let me move this transition a little so I have some space to do this. Still the same transition, I'm not changing anything, just grabbing some more space. Basically what this says is B1 equals prox and B0 and not B1. What? Well, wait a second. Think with me. If we're in this state, then B0 is a 1, right? And B1 is a 0. Okay? So if you plug in 1 and the inverse of 0 and 1, you will get 1. Do you see what we're doing here? We're not writing down a mathematical equation where we say we're now going to solve for B1. That's not what we're doing. This is more like your programming where you had a variable and you calculated a new value for that variable based on the current value of the variable. So we might have to say something like B1 new or something like that for this to make sense. I don't have room. Does that make sense? So this is just a logical equation. I can put this into a line of ladder logic. And what it would do is anytime I'm in this state, see how that has to be part of it? When prox is 1, it will change B1 to a 1, which should take me to that state. And you can say, well, what about B0? Don't worry, B0 will take care of itself. I know it's got to be turned off, but that will happen automatically. Okay, and I'll show you how in just a little bit. Right now I know B0 is a 1, I know it needs to be cleared. We don't have to worry about that part. All we have to do is worry about any place there's a 1. Okay? Now, let's check and make sure that this equation won't do anything in the other states. Well, that's pretty easy to see, right? If we're in the stop state, B1 is a 0 and B0 is a 0. So we'd have 1 and the inverse of 1, which will always be 0. 0 ANDed with anything, in this case prox, is 0. Now you can say, well, isn't that going to turn off the bit when we don't want it to? Actually, it won't. Again, you don't have to worry about the zeros. You just have to program the 1s. Because one of the beauties of this method. So this is one of our calculations, and you can look at this and say, well, that's all well and good. I see, you say I have to worry about ones, okay, that's B1 is a 1 there, it's a 0 there, I don't have to worry about it, it's a 0 there, I don't have to worry about it, but isn't B1 a 1 here also? It is. In fact, help me out here, we could write an equation for this one, right? It would look different than this one because it's in a different state, so it would look like this. B1 equals, well, what are the conditions? If I want to transition to this state, the only way to get there is from here, right? So what state would I have to be in order to get to this state? The box, right? Okay.
In your level.
And level has to be true. So what would the logic, what variable should I put in here?
Level.
Level.
And
And
not B0
not B0.
and B1.
You got it. Do you guys see why? Look, if we're in this state, that means that B1 is a 1. That means B0 is a 0. 0 inverted, ANDed with 1, is going to give us a 1. And if level's a 1, then we will get a 1 for B1, which is what we want to move to this state.
Okay, I was looking at the state below that.
Sure.
Yeah, I see what you're doing.
Okay. Now, you can look at this and say, well, wait a second. In normal math, remember normal math when we used to get to play? We thought it was bad once they started throwing the alphabet into math, right? But now we find out it's even worse once you have different bases, right? Well, remember in normal math, if you did a calculation, you said x equals 3 plus 2, and then you said x equals 4 plus 9, these two can't coexist, right? They're not the same thing. There's no way. Well, in Boolean algebra, all we have to do to satisfy both of these is just say or between them. Because look, we will not turn this into a 1. B1 will not become a 1 due to this part if we're not in this state. That's what this condition takes care of for us, right? So we don't have to worry about this part of the equation messing us up anywhere else because it references the state bits. And we don't have to worry about this part of the equation messing us up when we're here, or here, because we have to be in this state before level has any effect on the bit. Does that make sense?
Yeah. It's
So by combining the transitions along with those bits, then you don't have to.
So we've actually finished programming B1. Kind of stolen the thunder from Excel, but that's all it takes. For B1 is done. See, there's only, let's see, 1, 2 places where B1 is set to a 1. Other than that, B1 is a 0.
So if we had another state where we had, if we had another bit and another state, and we would need another OR, and we would need more conditions.
Right.
You just kind of keep adding them. So that's like one line in our ladder logic right there.
You got it. This is
Yeah.
one line in our ladder logic.
Yeah.
Okay. Now, you know what? I may not use Excel to do this because in the past when I've used Excel, it's gone a lot slower than this because you end up seeing all the zeros and I say you don't have to worry about the zeros. I think I'm going to skip that. So if you're watching the video, maybe there won't be a spreadsheet. I'll post what I've got because we've got a little bit here. It's just more cataloging what we're calling things than anything. Because I think we can actually program this very quickly and very easily. Let's try the other bit. Let's try B0. Help me out with B0. Where's B0 a 1?
And get box.
Get box, okay. So B0 is a 1.
Clear box.
How could we get to that state?
Only way you can get there is from
Clear box.
clear box or the stop state.
Right, so we could get there here, from here, or from here. Okay. All right.
You want to do the stop one first then?
Let's take care of stop first. I like that. Okay,
Yeah.
so stop. What should we write?
It-
We'll abbreviate this
Yeah.
and just start.
Yeah,
Okay.
start.
So start. And I'm sorry, I hope you don't confuse. Well, we called that the stop state, so we're good. Okay. So
And-
start and
Not B1.
how about if we take care of 0 first, which
Okay,
we've been putting that
not
first.
B0 and then not B1.
Right. Do you guys see how that works? Now, I'm going to pick on you guys, not to be mean or anything, but because during the exam, I want you to know what you're talking about. So we're going to go around the room one at a time and add to this equation, okay? Okay. So who wants to take it next? I'll give you that option.
Don't you move on to the next?
Yes, you're right. That takes care of
So then you want
this
to move on to
transition.
the clear box.
Good, clear box. So what should I write for that?
Let's see, proc should equal 0.
So inverse of proc, so we can get a 1 out of it.
Okay,
And we're ORing, right?
right.
Okay, so not procs.
And, not B0, or no, it is B0 and B1.
Good, B0 and B1, right? Because both of these are 1s. You put 1 and 1 with the inverse of 0, you will get the 1 that you need for B0.
Okay, explain this again, the
Sure.
inverse of procs.
Well, procs, the only time we actually want to take this exit ramp, this transition, is when procs is a 0. If procs is a 1, the inverse of 1 is 0.
Would be 0, okay, yeah, gotcha.
Right? Okay. Good, okay. Let's see, that takes care of this. Let's check off the ones that we've taken care of. We've taken care of all the B1s, right? Yeah. And now we just took care of that one, right? There were 2 transitions to it, so we've got that. Is there another place where B0 is equal to 1? Yes, right here. Okay. 2 other people that need to help me out on that. So we'll have another OR because we're still calculating this 1 for B0. How many ways can we get here?
Get to where?
One way. Get to here.
Where I did the fill box?
Well, yeah, we just finished fill box. That's what this bit was,
Okay.
right?
No, that's the
No,
stop.
no, that's not. That's the stop.
Yeah.
How did we get, oh, well, that's because B1, we're programming B0, not B1. B1 is up here, so we've taken care of that. We're just trying to make this one happen. How do we do that?
The only way to get there though is from the fill box.
That's right. So we have to go from fill box, good. So what do I write?
Level.
Well,
Level, good. And
Not B1.
almost,
You want one.
Okay, it'd be B1, not B0.
good. So not B0 and B1 to keep the same order, okay? Good. Make sense? That would give us this one. All right. Now this looks terribly easy, right? This is not too bad. There's there's 2 small problems with it so far, okay? So let's look into a little more of the details.
We knew there was a catch.
There's a little bit of a catch. This does take a little bit of time. This is why I usually went to the spreadsheet, but I think I've got enough room on the board to make this work. We'll have to put some of our equations over here, but that's fine. Here's the catch. The PLC scans, right? It goes through the code. It goes through, we're going to put these in ladder logic. It's going to evaluate these over and over and over and over again. It's going to do it very quickly, right? You're welcome to take a picture. I'll also take a picture of it and put it on Blackboard when we're done. Because this is really important. We need this later. This is our roadmap. This is how the program works. There's one catch. Think about it. If the PLC is in this state and it runs through these equations, it needs to be able to stay in that state. So there is an understood transition that is what I would like to call a null transition. In other words, by default, every state will simply go back to itself. Okay?
So like, while it's in that state, it's just like, it's not gonna move, it's constantly checking.
Right.
So after it checks, it's like, I'm still here.
Exactly
After this,
right.
I'm still here.
In other words, every scan, the PLC has to decide what state to go to. It always has to go to a state. That's all well and good, as long as we can go to the current state. That way we stay in the current state. Okay? So we're not quite done calculating the ones. All we've done is calculate the ones from the transitions. Notice how all of these have prox level start, prox see. Okay? So all we've done is taken care of the transitions. Now we have to program all the null transitions. Okay? So let's think about that for a minute. And notice, we do not want this to be based on the outputs in the state. Those outputs are going to be driven based on the bits, nothing else. The transition logic has to be based on the current state and the inputs. Okay? So we have some more ORing to do, but I'm going to put it over there because we're running out of space over here. And of course, all these would be new values, which is the other problem that I alluded to, but I'll show you how to take care of that in the program in just a minute. So let me move this out of the way and say this is start equal, is it 1 or 0?
You had it as a 0.
We had it as 0, but it should be 1, right?
I've got it written down as 1.
Yeah. Yeah.
So it was a 1?
It needs to be.
It needs to be a 1. Let's check. Our transition would be to go here. The only one it would affect is B0 equal 1. And sure enough, it would be a 1, right? Because this is not inverted. So only when start button's pressed and we're in the stop state can we go to this state. So that's good, that's good. All right, so we have to program all these ones again, but now for the null transitions. So let's figure out how to do that. If, let's see, we have to worry about this one, right? So B1, let me go back to the blue color. May as well start here. B1 equals, well, for this null transition, we would have to already be in that state, right? So it would be B1 not B0. But what would the condition be for staying in that state? Well, the opposite of getting out of the state, right? So, hope this is not off the video. In fact, I know it is, so let me move this over. B1 equals, let me put it in the right order, not B0 and B1, and not level.
But do you have to do that for each transition?
So you're
I
gonna
have
get
to do that for every transition, you're right.
yeah, so you're gonna get a 0 there.
No, I'm gonna get a 1. That way I can stay in this state. Well, look,
Oh, right.
The
because
box
right
is
then-
empty.
Yeah, you're right. Okay, you're correct.
the box is empty.
Yeah.
And so the inverse of empty is 1, right?
Yeah.
And so this will give us the B1 to allow us to stay. But you had a good point, Mr. Lowe. You said you have to do that for every transition. You're right. We have to guard against this transition too. Okay. So we also need an or if we're in the fill state. We do not transition if stop is 1. See, that's the opposite of that.
Okay, so it's gotta have a 0 to transition, so therefore you don't want it to, okay. Yeah.
Exactly. So as long as that stop button's not being pressed, we're gonna have a 1. We're in the state, that gives us a 1 so we can stay in the
So
state.
you basically gotta get every one of them wrong that you did over here.
No, we're just adding to it.
Kind of, we're adding to it.
Yeah, I mean, you sort of gotta,
There's-
like, if you was wrong over here, you'd be right on the right-hand side.
Okay, well, you've got one thing twisted there that I wanna pull back out, okay? You're thinking that these are basically the opposite of these, and that's not the case. These were all the transitions. We were calculating these bits from a different state. Now we're calculating bits from its own state. We're transitioning to the same state. See? So if you look at this carefully, you'll notice all of these depend on the previous state. Okay, if we're working on this one, it depends on the previous state. All of these will be the current state depending on itself. Okay?
So you'd have to change all the transitions opposite what they are, so they wouldn't cross over to the next state.
In a way, but notice that over here where I have level and here not level,
Yeah.
notice the conditions for the, wait a second, no, they don't look different, do they? What's wrong here? Hang on, let me think for a second, make sure I've done this right. Because this should be a different state. We're calculating, oh, it's because it ended up. No, actually, okay, here's the distinction. You're right. Because this is the same as that, isn't it? All I've got is this different. I don't think it's gonna hold every time. If it does, I've done something wrong, I think. Okay, so we'll see.
Cause that would have been for the above, yeah.
Because see, I think this was this I think was the calculation for this B1 being on, not this B1 being on. Not for this state, but for this state.
Alright.
It just so happens both these states have a 1. Okay? That may not always be the case. Sometimes we may want to go over here, right? And in that case, B1 is a 0 instead. So I don't think we're going to get just the opposite of all of these. It just happened in that one case. Okay? Now, let's continue just a little farther. That takes care of keeping us in the fill box state for B1, because again, we don't have to program zeros. Okay. Let's program, since we're working on B1, let's program this one. So if we're already in the state, how do we transition and stay in the state? The only transition out is prox equals 0.
What about, shouldn't the last one, the fill box, shouldn't we program for the prox state? Or for the prox transition?
Shouldn't we program this for this?
Yeah, to not go back.
No, because there's no way to go back here. The only choices we have is to either stay in or go this way or go this way.
Okay, yeah, I see. All right.
Good question. Anything else? Okay. So now let's program this one. Okay, this is what we're going to work in, because we're working on B1 anyway. And of course, I should write, this is the new value of B1. Okay, so let's program this one. How do we do that? Well, help me out. We're in this state, so or, what would I write?
B1 and B0.
B0 and B1, good.
Yes, sir.
Because both are ones.
Yep.
And
And
what else?
stop, and not
Prox.
stop, or stop.
And prox.
And prox.
We're only worried about the ones coming out, right?
Yep.
You're right, Mr. Lowe, that there's another one, okay? So we have to write or B0 and B1, and we're gonna take care of this transition. We're gonna block this transition, okay? When stop is the opposite. So, Mr. Lowe, what were you gonna suggest?
Just stop.
Stop. Because when stop is equal to 1, we want to stay in this state. We don't want to take that exit ramp. Okay? Now later on, what you'll see is there's a lot of simplification we can do with these. That's where the Boolean algebra comes in. Okay? Well, we'll do it graphically. It'll be a lot easier. Okay?
I thought we were going to go a day without saying that.
Could have gone all day without hearing the word Boolean algebra. Okay, so what have we done? Well, we've taken care of that one now, right? There's no way to get out of this state, or we've blocked the transitions out if they're not appropriate. All right, last one. We have to work with B0 here and B0 here. Since we're in the state, let's work with it first. So B0 new is equal to what? I'll let you guys tell me.
Is equal to not B1. Oh, sorry, B0 and not B1.
Try again, B0 and
B1.
B1. They're all ones.
Oh, wait, I was looking
In
at the wrong
this
place, I
state.
think.
And no
Okay.
props.
It can get really confusing really
Yeah.
quick. It's okay.
And props.
And prox, yep. Because we have to block that transition. What else?
Oh, okay.
It's the same thing with stop.
That's right. Or B0 and B1 and stop. Okay, so that takes care of this one. But we have another or here. In fact, it looks like there are 2 ways to go there. In fact, did I miss one anywhere? I don't think so.
No.
No, because, the stop state is 0, 0. That's what made it so easy. Okay, all right, good. All right, so 0, 1. So how do I program this B0 here? What do I do?
B,
The B-
B0.
or?
and- Yeah, or B0.
B0
And not B1.
and not B1.
And negative, no props.
And not prox.
That's right, and not prox. We're blocking that one. Are there any other transitions we may need to block?
For this stop button.
Stop button, that's right.
Yeah,
So what
so-
would we do there?
Our B0 and B1 will be the same.
Yes. Or B0 and not B1 and
Stop.
And stop, if stop is 1.
how about, let's see, let me think. Yeah, stop is 1, because it's the opposite of that. Yeah, good. Okay. Now, over there we've got a B1, over here we've got a B1. Which one do we use?
You use them both, you add them up.
Or them all
Yeah.
together.
Yeah.
Okay, same thing with the B0. So we're gonna have one rung for B0 and one other rung for B1. Okay, it's gonna be a mess. guess what? If you make one mistake anywhere, nothing works. Everything is confusing, okay? Well, sometimes it kind of works, but usually it just doesn't work well at all. So, it's a little bit of a long process, but do you see how developing the algorithm is more about deciding what states the machine should be in and when it should transition between the states? Which is a really nice way to develop an algorithm, because it's basically the same algorithm every time. Just leave the machine in a particular state, let it keep doing something until that task is done, like filling the box, and then move on to the next step. Okay? Which is really nice. Now, the power of this, you might say, well, this is the same thing as the list that we did before, right? Well, the difference is that in a state transition machine, you can move to any state you want at any time that you want. You can be in this state and decide there's some condition for just going back to the get box state. No problem. Add a transition, add the equations, you're ready to go. Okay, so it's fairly easy to program as far as the algorithm development goes. All right, so for those of you on the video, I'm going to move over to Logix Pro, and of course I will post this program for you so you can look at it. All you will see is unfortunately the end result. But all I'm going to do is put in 2 rungs of ladder logic so that I can put B0 and B1 in as ladder logic. So let's do that. So 2 rungs, I'm just putting 2 outputs on the rungs, and I'm putting B:0/0 on the first rung and B:0/1 on the second rung. The first one I will call state bit 0. The second one I will name state bit 1. Okay. Again, it's up to me to control these bits so that the PLC does the right thing at the right time, and that's what this code is all about. Now, notice that B0, I'll start over here on this side, and I'll just go line by line. I've got 1, 2, 3, 4, 5, 6 OR paths.
So
Okay?
I need a whole bunch of branches.
Well, actually 7. So I need the straight line and I need 6 ORs. Okay? 1, 2, 3, 4, 5, 6. Okay? Got 6 OR branches, 1 main path. The main path, I'll just put it in order. I'll put the start, not B0, not B1. Okay? So start button. I'll have to label it. We want not B0 and not B1. Do you see why I'm using the opposite set of contacts, the XIO? Because I need to invert the bit, right? Oh, actually here, hang on. It should be B0, B1, okay. So that address is here. And here, there we go. Do you see how that first, I'm looking at rung 0, I'm looking at just the straight across top ladder, or top rung. Do you see how I've just copied this down basically? Start and not B0 and not B1. Okay. So you guys help me out. For the next one, not procs and B0 and B1, what should I put in?
It'd be the 1-03, be not that,
Okay, good.
and then it would be B0, B1.
Good. So I will need, what are these called? Examine if closed for B0 and B1, and I'll need examine if open before that for procs.
Correct.
Okay. Now I have programmed this bit. What about this one?
We're gonna need the local level sensor, and I'll need to be an examine if.
Here's what I start thinking about. I start thinking about non-inverting, inverting, non-inverting. That way I can set up the structure. Okay, so non-inverting, inverting, non-inverting. And if I just put everything in the same order, everything comes out okay. So level, I1/4, let me edit the symbol.
Are you posting this also?
I will post this also, yes. Okay, so level, not B0 and B1, I've got in there. The next line, notice, is just three, I can never remember which is which, examine if closed, three examine if closed in order, right? So three non-inverting. And they are, I'm gonna flip them around. I don't know why we put our sensors last in here, but we'll put them first. So the first one is procs, and then bit 0 and bit 1, the state bits. Okay? So that takes care of that first line on B0. The next one would be stop. And B0 and B1. Okay, now you guys tell me what to do for the next two.
Not procs,
Okay? So
and
inverting for procs.
invert bit 1, and not invert bit 0.
So don't invert bit 0.
Yes.
Does everybody agree with that? Okay. There we go. Somebody else, the last line. What do I do here?
You need a normal, you need a normal, and then you need an inverted in that left to right.
Okay, so how about a normal? Yeah, you're right. You're
Yep.
right, because we're putting stop first. A normal and then an invert. Good.
And then just drag it down.
Drag the stop down, drag bit 0, drag bit 1. It's a mess, huh?
Actually, it's pretty, seems pretty simple.
Pretty straightforward.
Today.
Yeah. It's really not too bad. I think before, the reason students were confused is because I was using the Excel spreadsheet. There are a bunch of zeros we didn't have to worry about. So this may be a better way of showing it.
I think I might have an easier way of writing it.
Okay.
Like to start with, to make it kind of all line out.
Okay.
But, like whenever you're, like, you pick a side to start on, do everything for state 1, including the nulls.
Yeah.
And then, so you can group them together, and then move on to the next state, and then do that, and then have it all